Hello, friends. Welcome to the Nexus Podcast. I'm your host, James Dice. Each week, I fire questions at the leaders of the smart buildings industry to try to figure out where we're headed and how we can get there faster without all the marketing fluff. I'm pushing my learning to the limit, and I'm so glad to have you here following along. This episode is a conversation with Rob Brimblecombe, Manager of Energy and Sustainability at Monash University in Melbourne, Australia. We talked about the university's net zero initiative and how that has driven changes in the way their buildings are designed, operated, and of course, how it changes the technology that runs them. This is a fun one. Please enjoy. Hey, Rob, welcome to the show. Can you introduce yourself?
Thanks for having me, James. Great to be here. Yep, Rob Brimblecombe. I head up the engineering and sustainability at Monash University in Melbourne, Australia.
Cool. And can you take me through your background before you got to Monash?
Yeah, absolutely. And I guess the reality is that there's not much before Monash in terms of, I actually studied at Monash many years ago, but there was a little bit in between. So I guess professionally, I started out in a very different space. I started out in plant genetics, actually looking at how plants manage energy, or at least that's the story I tell. And they are very analogous to buildings, which is, I guess, why I brought it up today. And you might be familiar with the Living Building Challenge. They talk about this metaphor of being rooted in place. And it's a good metaphor, but it's actually richer than most of the story goes in terms of the plants we were looking at. Actually studying tobacco, which sounds a bit strange, but it's a well-studied plant because obviously there's a fair bit of money in tobacco, or at least there was. But the point of the story is that plants generate their own energy. They've got to regulate their own energy. Obviously, they're not generating overnight, just like buildings aren't. And amazingly, plants talk to each other, both through their root systems and through the chemicals they release through their leaves. And they had this incredibly complicated control system where they're always optimizing for growth, respiration, reproduction, and for defense. So I guess the story of tobacco is that the nicotine is actually a poison to stop bugs eating them. So they don't produce a lot of nicotine naturally. What happens is if you chew on them as a bug, or in my case, if you cut the top of the plant off, they send these signals down to the roots and they start producing the nicotine. But the nicotine is incredibly energy intensive, so they don't do it lightly. So I guess it's this really nice analogy for me around plants are generating this precious energy resource. They're trying to manage it for their own requirements. And then when they have to, they'll produce these other compounds to defend themselves. So it's really similar to our buildings in terms of they're rooted in place. Obviously, we can power in from other areas. We're communicating with other buildings. But how do you optimize your resources to get the best possible outcome, in our case, for the building occupants? How do you provide the fresh air, the clean water, the nutrients that our occupants need to be productive? And how do you do it in a clean way that it doesn't rubbish the environment that you live in? So from there, it was an obvious jump into energy management. So I did more the traditional energy management degree, did the solar and wind, and then combined the two and went and did a PhD in artificial photosynthesis. So there we were really looking at how plants capture energy and trying to replicate it. The incredible journey and incredible thing to research, but it turns out that plants are really good at it. They've got 50,000 years on us. And the trick that plants do is that they have these incredible enzymes that run hard, generate energy, split water, produce effectively the protons that turn into carbohydrates. We were trying to produce hydrogen out of it, and we could do it. But what plants do is they burn hard and fast, and then they regenerate, which buildings can't do. And I think this is part of the question that you often ask of why is the technology so far behind? But the difference that plants do is that they constantly regenerate their technology, whereas our technology, our solar panels, our controllers are fixed in place for 20 years.
Totally.
So we're successful in the research. We managed to generate hydrogen for at least 90 seconds before the whole device self-collapsed and needed to be remade. So like I said, it was a fascinating research topic, but really what it came down to was that hydrogen, as it was then, was still 10, 20 years away. And as we know, it's creeping closer, but it's still a bit of a pipe dream or a bit of a moonshot. And I had this pivotal moment, as for many of us do, where I was studying at Princeton and Amory Lovins came in to give a talk and had a dinner at one of the halls there. And I'd been a fan of him for so many years, and all the concepts of tunneling through the cost barrier and that the people are the most important investment in the buildings. But it was just really being there in person and hearing him talk that made me realize that the solutions to all the challenges of climate change and better buildings, they're all out there. It's just good science. But the trick is putting all the pieces together. And it was really that moment that, I finished up the PhD, and then jumped into effectively building management at Monash University in Melbourne, back to my roots where I did my undergrad. And I've been there for the last 12 years, really working on that journey.
Very cool. That reminded me of when I was in basically the concept of biomimicry. Is that what they call it? Yeah, the biomimicry concept reminded me of when I was in high school and college. I used to read this blog called Tree Hugger, and I don't even know if it's still around. I haven't read it in a long time, but it's one of those things that like introduced me to all these like sustainability ideas before I knew how the actual world worked and how buildings work and how economies work. And so I just always look back at that time like, oh man, I used to think things like, biomimicry were just the coolest thing. And then when I got into the real world, it was like the real world was so far from being able to make a lot of that happen. Like my first job was at a mechanical contractor, for example. It's like, you can't even say the word biomimicry at a mechanical contractor. So anyway, very cool. And I want to give a shout out to one of your consultants at the university, Kieran, who's a student in my course that kind of gave me some background on all the cool stuff you guys are doing. That sounds like you and Kieran have a weekly debrief after you both listen to the Nexus podcast every week.
Yeah, that's it. Poor Kieran, he knows when the call comes to clear the desk because there's a window of time that he needs to. We joke that he's got an app on his phone that he turns on when I call, and it just starts billing against the Nexus podcast. He just puts his timesheet down as Nexus debrief. But certainly whenever those new ideas come in, the new words, the new companies, then I ring him up and say, Kieran, how are we going to do this? And Kieran's been great because it's an evolving space, and it's impossible for one person to know it all. But every time I throw a challenge at him, he's like, all right, let me at it. I'll come back to you and we'll see what we can do.
That doesn't surprise me at all. Very cool. Well, he told me about a lot of stuff that I want to unpack with you. And I mean, you sent me some stuff too that looks awesome. Can you just first start with an overview of the university and just sort of provide some context of, what kind of buildings we're talking about, how many, that kind of thing?
Yeah, absolutely. So Monash is normally Australia's largest university. We have about 60,000 domestic students or Australian-based students, although that's been a little bit different over the last year. We've been far more global in our nature with students studying from around the world. We also have some campuses across Asia and a small one in Italy. So we're very large, and I guess compared to, say, Princeton, which is, roughly, when I was there, about 5,000 or so undergraduates, 60,000, it's a city. So we have all types of buildings. We have the resis, we have high energy research buildings from biomedical to wind tunnels. We have a synchrotron sitting on the site next to us. We've got commercial buildings, we've got office buildings, lecture theatres, although they're sort of a bit mothballed at the moment, and big tutorial buildings. So it's, other than sort of heavy industrial, it's a spread of what you find in a city. And I guess the interesting bit about them is that they're often on one grid connection point. So our main campus, about 80 buildings, which is where on a given day you can have 40,000 students coming through all the buses and traps, but it's connected to the grid in one place. So I guess we have this little micro environment, our own little network that we can play in. And then I guess if you think about the scale of it, across the Australian campuses, we have about 160 buildings, about 680,000 square meters, or I did a little calculation. I think it's about 7 million square feet in your terminology. So there's some there's some scale there. Yeah. And I guess the journey for me started with, how do you chase the low hanging fruit? As so many of us do, you got to get your early runs on the board. And pleasingly for me, there was pneumatic controls in the space. I went in, ripped those out, put in DDC, and you get that instant 20 to 30% energy savings overnight. Then jump deep into the retro commissioning. Again, there's really great savings to be had in a building, in an environment you're running hard and fast every day.
Totally.
And then we did a whole bunch of Green Star, which is our lead equivalent buildings, the buildings, new builds. So getting it up to that sort of new standard, and chase the sort of low hanging fruit as they came on of LEDs and solar. So it was this great test and learn environment for me. I came from a slightly different space, so I really got my engineering degree actually practicing it. But
And what
eventually
year did that start?
it was about 2010 when I kicked off in the actual energy management space.
Okay.
Plenty of learning to do. And I guess back then, with the pneumatic control upgrades, I know it wasn't new, but the big thing for us was a backnet standard. Let's get everything on backnet, which we'll pick up again on later. But so we rolled out a huge amount of new controllers, a whole amount of backnet, which I wouldn't say we're unwinding, but we're certainly trying to put in its place. And I'm sure we'll get back into that in a bit more detail.
Were you at this point, like the term we have in the US is like campus energy manager? Is that what your role was? And I guess part B of that question was, did you guys have like we're setting a 2010 baseline and we're looking for 20% energy savings, or what was it back then? Because we'll talk about what you're doing now in a minute, but what was the sort of impetus for this?
Yeah, you've almost hit it on the nail on the head there. That my title was energy and water manager, and we had a 20% energy saving per floor area or per student load was the kind of goal. So recognizing that universities are heavy energy users, in terms of when you run a lab building, it's never going to be net zero energy standalone with the solar on the roof, because they're sucking energy through the fume hoods and they've got deep freezers and all that sort of stuff.
Yep.
But yeah, the goal was to bring the energy down and make us more efficient. And it was that kind of first step. So we had a lot of luck in that. And I'd like to say hit our goals. We came pretty close, but by the time we hit the target, we were sort of about 18 or 19%. So well and truly in the ballpark, that enough that people didn't question us and they let us get on with it.
Totally. Okay.
The other advantage of working for the uni is that we are an education organization. We've got the R&D behind us. So I had this great opportunity to teach into it as well. So, it's this great opportunity to practice and actually teach into the students, and also this ability to learn, which we've talked about previously. Of a lot of commercial entities don't have that opportunity to say, all right, I'm going to try this high temperature oil-based heating system on the roof of the building that's got 200 valves and 5 pumps running through it. That's just horrendously complicated and no commercial real estate manager should ever touch. But because we're a university and we've got the mechanical engineers, we gave that a go. And for the record, don't do it. It's too complicated.
Yeah, even if you have the engineers, don't do it. That's hilarious.
So I guess off the back of the 20% target, we, again, working with the students, the advantage of students is that you can get them to do exploration work, and that they're thinking outside the square. So I set the students from my course the assignment as their final year research project. Can we get the university onto 100% renewables? So I said, and don't just think electricity, think the whole thing, because gas is about just under half of our energy consumption. Obviously, boilers are far more inefficient than our cooling systems. So overall, in our climate, which touches sort of freezing and, on a hot day gets up into, the hundreds or up into the 40s for our Celsius. But we have that sort of extreme. It's not as extreme as some of the places, obviously, across the States. But we do have those extremes and then a nice period in between. But still, we have a solid heating load, in our traditional buildings. We're a heating-based climate. So they had this challenge of getting off gas, and they did this amazing assignment, which, when we landed it to the university executive, they were just like, what the hell is this? You want us to jump to 100% renewables and you want us to rip out all our gas, which would have been back in, 2016 or something, where people were talking about it, but people weren't really doing it.
Yeah.
So to be honest, it kind of, I was pumped about it and the students were pumped about it, but it kind of sat on the shelf for a couple of years. So I went away and wrote a book on positive energy homes and licked my wounds of the university executive saying no. But eventually the time came around again and we got a new vice chancellor, which is the equivalent of our CEO. And she said, climate change is one of the most important global issues of our time. I'm going to lead an organization that's making a difference. And we want to offer degrees that don't cost the planet. So she said, set me a net zero target. And I'm like, oh, here's a nice little plan I presented earlier. But that leadership moment is critical, and you look at those history shows that the leadership is critical. So she came out and said, do this, and we served up the plan in 2017, and she took it to the council, which is the equivalent of our board. And from there, we set the goal of 2030. We wanted to get off gas, and we wanted to be powered by 100% renewable. So at the time, lots of organizations committing to carbon neutral, lots of them committing to 100% renewable electricity, but few committing to really making this transition as a whole. And since then, pleasingly, lots have jumped on board. Not saying they followed us, but I like to think that. Lots of people aiming at it, but certainly a lot of heavy lifting, and hence the 10-year program to get there, to change out all the infrastructure.
Very cool. 2 questions. So you just glossed over the fact that you went and wrote a book. Well, tell me more about this Positive Energy Home book.
Yeah, so I guess it was, as you know, and as many of your listeners will know, working on buildings, you kind of start with the controls and the kit. Can I make the kit run better? And I'm sure many of your listeners have had a crack at changing set points. And the big lesson for me with changing set points was that you think you've got a deadband of 2 degrees because that's what the building automation system tells you.
Mm-hmm.
But in the building, it's more like 5 or 6 degrees.
Oh, yeah.
So we did a program one year where we said, we can save a whole lot of energy, and you can. We worked out about 6% per degree of set point deadband you increase. But when you go from, a couple of degrees deadband and you change it a little bit, the building blows out. Mm-hmm. And you get this, broader range of deadband. So, effectively what I ran up against again and again with trying to tune mechanical systems was, I had single glazed, unshaded windows. Mm. And I don't care how good your HVAC system is. If you're sitting next to that, the radiant heat is just killing the occupant. And then likewise in winter, you've got drafts falling off that window, and the temperature sensor on the wall might say it's perfect, but the person in the room is experiencing something different. So I guess I got really deep into building physics.
Okay.
And again, teaching it helped me refine it. There's nothing like standing in front of 50 certain final year engineers and having to know your stuff. So I really got deep into that. I got into the Living Building Challenge and their positive energy or net zero energy buildings. Bullet Center was my hero for many years there. And I guess effectively said, all right, there's a knowledge gap here for me, and let's put it into a book. So lady Cara Rosemore from New Zealand, who's a passive house guru, her and I wrote the book about how you do this for homes. And homes are low energy density. You have 3 or 4 people in this huge space. You got plenty of roof space. So if you create a home where you're managing your moisture, you're creating a comfortable environment for your occupants, and you're pumping fresh air in, which is critical. The idea of pumping air into homes is still a strange concept for most, but she did her PhD on air quality. So she had all these graphs of just diabolical CO2 levels in bedrooms and all these things. So it really came together for us of this is where we spend our lives. We've got to put this information out there, and I guess it was the home is a simpler approach. So we started down that path and, had this wonderful experience of writing a book. And it really set the tone for how we approach buildings at Monash from there. And I guess after that, we started the big challenge of trying to build passive house at scale. Homes are complicated beasts, but they're nothing like a big, complicated lab or teaching building or office building.
Right.
Actually, the forward of the book is from the guy who ran the Tree Hugger blog. Actually wrote the forward for our book, so it links it back nicely together.
Oh, that's great. Oh, so my second question was how you're defining 100% renewable. Does that mean you're able to produce or purchase offsets, or is it 100% renewable electrons coming directly to your end uses?
Yeah, great definition. So what we defined as is net zero, and Cara, my co-author, always hangs it on me for net. She's like, net doesn't work. If everyone does net, then the grid doesn't work. But how do you explain to people? So we needed a tagline. We needed something that we could stand behind. So we went with net. And I guess net zero emissions for us means that on an annual basis, we are generating or putting as much renewable energy into the grid as we're consuming. So for a research heavy organization, for buildings that have students in them, 12 hours a day going hard at it, and incredibly high energy densities, or at least pre-COVID, it's just not possible for us to generate that much energy. So we did the maths and worked out that best case, if we covered every single roof space, which as we know is not possible because there's plant on there, there's asbestos paint, there's all these complexities on roofs that you just never dream of until you get into it.
Yeah.
We could probably generate about 10% of our total energy requirement.
Wow.
So the big balance of it is get as much out there as we can. We've got about 4 megawatts of solar on our rooftop now, but the balance is through a wind farm in Victoria, which is the state we're in. So we've got about roughly 30 megawatts of effectively leased wind turbines, where basically the generator there, obviously there's a company that runs it, RES, that runs the wind farm, but we effectively own the electrons, which we sell back into the grid, and then we retire the renewable energy certificates, or at least a portion of them, as we transition up to renewable energy. So there's a two parts to net zero of you've got to generate enough renewable energy, either directly or indirectly, to cover your loads, and then you got to get off the gas. And in our case at this stage, based on the technology, make everything electric. I'm very open and happy to have the arguments that will come around the role of biogas or hydrogen in the future. But right now, you just can't beat a high efficiency heat pump.
Totally. I actually thought of the third question I had before we kind of dive into the more of the specifics here. The students that wrote that plan, back in 2016, what are they doing now? Are they doing cool stuff? They sound like some smart people.
Yeah, they were absolute pleasure to work with. So they've gone on to great careers. One of them works for Arup. She was doing all sorts of great environmental studies around them. And I think last time I checked into her, she was over in Wales working over there on this type of work. One of them I selfishly held and kept for many years, and he helped me develop up the whole net zero program. Tim Hoban, absolute gem. And Tim's ability for me to throw something out there at him and he'll go, I'll give it a go. Blindly ignorant of how hard it was, but he's like, he didn't know, so he just got on and did it. It was an absolute winner. He's now at the City of Melbourne helping with basically them on their journey now, which is a really great outcome.
Great.
And then the other lady, Jo, she went on and now she's working in the traffic and roads development across Melbourne. So a really successful engineer in her own right now. So
awesome.
Getting a little emotional, but as you would be experiencing with your courses now, seeing the students that you influence go on and do great things is really pleasing.
Yeah, definitely. It hasn't quite, I think of it like a snowball, hasn't quite snowballed enough to that point yet, but there's a couple of early indications with our course that's, I'll probably be tearing up here soon. Cool. So I want to talk a little bit more about the net zero initiative. The people that are waiting for the normal technology discussions, we'll get there in just a minute. So you talked about sort of procuring the PPA of the wind farm. Let's talk about eliminating gas. Like, how are you approaching that? Obviously, for a new building, it's a design problem. I think more of what I'm wondering about is, let's just unpack new buildings first. I'm assuming it's, like you said, air source, water source, heat pump approach for heating. Is that the approach?
Yeah, so as you say, new buildings much easier, and we were lucky that at the time we announced the university was going through a building boom. So I had a whole series of buildings that I could crack this nut with. So we've now got 4 at scale buildings, and when I say at scale, we've got a teaching lab, we've got a very large education building, we've got 150 apartment resi college, and a 5-story office building that have all been built to all electric, and at least 3 of them built to the Passive House standard 2 with certification. So it was just this really lucky time where we got to explore and frankly got to transform the industry, because no one was building like this, and engineer after engineer said, no, you can't do it. I'd find these case studies from around the world, and I'd find the engineer that had done it, and I'd join the dots and say, they can do it. Why can't you do it? So I'd really set this challenge. But I guess the Passive House standard, comfort first. And for those people who aren't aware of it, I think that maybe it's just a quirky German standard. I like to root it back into the physics. The whole premise of Passive House is that you need air to breathe. As we all know, good air quality. So they work out how much air you need per person per hour to do that. And then effectively, the rest of the design is built off that. So basically, for a home, you need about 30 cubic meters per hour. Sorry, I don't know what the translation is.
Okay.
And they say, okay, you've got to deliver that somehow into the home. And that's your energy budget for heating and cooling. So the amount of heat that you can squeeze into that 30 cubic meter of air is how much energy you should be allowing yourself for heating and cooling. And then design back your building envelope so you can achieve that.
Okay. I think that's 15 CFM. And just math in my head real quick. I think that's 15 CFM for US based people.
Thanks for the translation. So then, and you've got to create radiant environments that are comfortable. So you're making sure your surface temperatures aren't dropping below a certain temperature. So you're not getting the cold experience of sitting next to a window, and critically, so you're not getting condensation forming, which leads to mold and, obviously degradation of indoor environment quality and the degradation of the building itself. So if you think about that from a passive house point of view, you are getting right down to very low heating and cooling requirements, which makes it much, much easier to electrify your building.
Okay.
So that's kind of where we started. Get the envelope good and then reduce your heat loads. That doesn't help you if you're running in an anatomy lab and you need to flush the building full of air all the time because you need to flush out the formaldehyde or whatever it is that they use to embalm bodies and such. So I guess where we got to was looking at all the different tricks that you can do to reduce that heating load. So heat recovery ventilation, it's sometimes questioned as, is the economics there? We're finding that in our climate on an annual kilowatt hour basis, it's probably not, but on a peak demand basis and on that keeping people comfortable, easy, and reducing your chiller size, reducing your heat pump, it's worth it. So I guess getting to the heat pumps, if you reduce your heating load, and in our case, we've got one building where we actually don't have any active heating anymore. We just use heat recovery. We use the occupants of the building to do so. And I'll touch on that again in a moment because it's had its challenges.
Okay.
But get your heat load down and then use your heat pumps. And again, in our climate, air source is a good option. We don't have, on our sites, we don't have a good groundwater base. It's too deep down. So we haven't been using geothermal, but I've seen really great examples up in North America where tap into the ground and you've got a really good source of effectively heat for your heat pumps. But heat pump technology, as we know, is far more efficient than a boiler, that can run down in the sort of 60%, whereas these things have got that COP up in the 2.5, 3, depending on your temperature range. And I guess what we've found is that with the right refrigerant, these new CO2 heat pumps and those type of things, especially for domestic hot water, it's been relatively easy once you get the engineer convinced to do it. And I guess the other challenge is that it's a different control strategy. We all know about split systems that can go back and forwards, but when you're talking about a full commercial scale heat pump on the roof and switching between heating and cooling and buildings that want a bit of heat, a bit of cool at the same time, dual duty on that plant, you've got to think it through. But it's all very doable. And I guess then jumping to what I'm imagining the second part of your question is how do you do it for the existing buildings, which the new buildings were easy. Like I said, we almost don't heat them. They heat themselves from the inside and you just manage the heat load. Basically, you're extracting heat. And in the Resi College, which hit Passive House Standard, like I said, it does most of the heating itself. It's been incredible to watch that building perform. The temperature variations in it on a sort of 24-hour cycle, a few degrees, if that, a few degrees Fahrenheit, a couple of degrees Celsius. And the empty building drifts very, very little. So the physics works, basically, no surprises. And we found in the winter months when the students go, we have about 3 or 4 weeks off in the middle of winter where the students go back, visit their family and stuff. So the empty building became a problem for us because we no longer had our heaters, being the showers and the humans. And we found that we put about 5 panel heaters that you just buy from your local appliance store around the building.
Okay.
And it heated the whole building. It was incredible.
Oh. Okay. So
and
you
my
turn everything off, seal everything mechanically, and then just turn some, all right, plug them in the wall.
Well, even we were pumping fresh air through the whole time because there were still students there. So, but just that little bit of heat top up was enough to keep the building comfortable.
Got it.
And it also gave variety in terms of there's one student who I saw in the data who I'm assuming came from a tropical climate because they run their room with a little portable heater at about 26, 27, which must be sort of 70 in Fahrenheit. Okay. They like it warm. And then another student who left their window open all the time and kept it cool because they like it. So it really gave this great diversity for people to have the option. But anyway, coming back to electrifying new existing buildings, the challenges come of your coils aren't designed to take the cooler water temp. We have a high temperature hot water loop at one of our campuses. So we're pumping very high temperature water around the campus. Don't know the conversion, so I won't even try. But the water temperature into existing buildings is typically higher than heat pumps will provide. They're getting better, and you can cycle them up and do multi-step heat pumps. But I guess the challenge for us is in some cases putting in new coils. So you have a bigger surface area, so you can use the lower temperature. But I guess getting back to some of the tech is improving your control strategy. So you're getting the heat in at the right time and you're preheating and doing all those kind of tricks. But for us, it's a case of trying to electrify that plant in a kind of precinct scale, because replacing every chiller and every boiler is pretty challenging. So we're doing clusters of buildings. So we'll take, say, a science cluster of buildings, we'll take the resi cluster of buildings, and we're doing centralized plant, which introduces some energy losses, as we know, but it allows those, I guess, the cycling of heat pumps on and off, and it also allows the economies of scale and the dual duty and the partial loading of your chillers and all that sort of good stuff. But it allows us to effectively provide all electric, renewable powered hot and cold water to these buildings, and then either through some upgrades of the heating distribution or through better control, we're finding that you can start that transition. Ideally, you retrofit and you insulate the building and you make your job a lot easier, but as we know, that's expensive and just not realistic for the vast majority of buildings we have out there.
Totally. Are you looking at electric resistance to kind of supplement things, or how does that conversation work?
I'm going to guiltily admit that one of the things I did when I started in energy management was ripped out electric resistance heating and put in gas because it was lower carbon. That's what you did 10, right. 12 years ago.
Yeah, I've done it too, just so you know.
We're on the same page. We're both guilty of that little gem. I guess the trick there is that, and it's this balance between, I used to chase kilowatt hours and now I'm chasing renewable energy. So resistant electric is still far more efficient than gas. It's almost double once you factor in the pipe losses and all that type of stuff. So from an efficiency point of view, it's not as evil as I used to think it was. It's just not as good as a heat pump. And if you're powering it by relatively cheap and potentially zero marginal cost renewables, where I hope we get to, then it's not a terrible outcome. So you've hit the nail on the head that some of the strategy can be that you pump in your heat pump hot water, but if you need a top up for that 20 minutes in the morning where you're doing the pre-cool, once the building's warmed up, we're good for the day. It's just really that sort of 7 a.m. warm up on a cold winter's morning that you really need to hit it. So in that case, using a bit of electric for really probably less than 10 hours a year for some of these buildings, it's a cheap, effective, and super easy to control solution. So again, I argued in the book with my co-author. She's like, "What's wrong with resistance?" I'm like, "It feels wrong." And she's like, "But you're only using 100 watts to heat a whole house. So what's the big deal?"
Who cares?
In the passive house case. So yeah, we're playing in that space.
Yeah, I think it's sort of a no-brainer from the standpoint of especially a retrofit, where you could make a choice of extremely expensive coil replacements, or you could supplement things here or there. Cool.
So I guess, and touching on that, the cost, you don't get to net zero without some investment, and there are costs associated with it. As we know, the infrastructure is a big shift, as we've been talking about. But this dream of zero marginal cost energy, we're not quite there yet. But in parts of Australia where we have great renewable resources, it's starting to play out. We're starting to see the start of this market where you can get free or even energy that people will pay you to take. So there's this great example where South Australia Water, which is effectively the utility that provides water to South Australia, as you would expect, a state in the south of Australia. And South Australia is really leading the world in this space. They're up to about 70% renewables, and on a given day they can be entirely powered by solar or wind. They're connected to the broader Australian grid, so they do have that backup. But in this case, South Australia Water has a whole bunch of pumping infrastructure, has a whole bunch of storage infrastructure, which they can generate power off. And I guess this flexible load, because the dams need to be topped up and the water needs to be supplied, but it doesn't have to happen instantaneously. It can happen at different times of day. So rather than net zero emissions, they're going for net zero energy costs. So they're playing this game where when they've got excess power, when the grid's full of power, and indeed when the market goes negative, which it tends to do relatively regularly over there, they pump and they store up. And then when the grid goes hot and they need to turn down, they do so, and then they start exporting. So the idea is that they can make more money through exporting energy than they spend through consuming energy.
Wow. Okay.
Or even they can make money through consuming energy because, like I said, the spot market goes negative. So we're not there as a university. We have nowhere near that kind of control. But that's the premise that we're running for, that in a marketplace where if you have that flexibility, you can take advantage of grid spikes and you can turn down and make money. You can share it with your retailer. And one of your podcasts touched on this, the value left on the table. And also, when energy is cheap, you can crank up your wind turbine, you can store up your batteries, you can heat your buildings, all those type of things, and be in a position where you're running a high energy university. So I guess there's this balance for us of how much energy can we save, which is just, money on the table, as we know, but how much flexibility can we build into our city so we can start playing in this increasingly renewable powered and low cost grid. And we've seen the energy price collapse over the last year or so, which primarily is from a reduction of global gas. So gas was driving our energy market prices and they were through the roof. We were paying ridiculous amounts for gas and it was driving up electricity costs. But renewables have flooded into the market and gas demand across Asia has dropped off and our gas prices have gone down. And now we've got all this renewable energy in the grid and the energy prices have really backed off. So we're seeing a world where it's increasingly renewable and it's getting cheaper and cheaper. So being able to play in that space and make the most of the grid services revenues and being able to maximize cheap energy and respond to expensive energy comes, I guess, to the core of your podcast, which is good control means good economics for your buildings.
Right.
And I guess that's how we're selling this transition to net zero. It's the right thing to do. It's the position for the university. But at the end of the day, so far, other than the heavy investment in plant, which we needed to do to keep our buildings running, being powered by wind energy is saving us money because it's cheaper than the grid. And obviously our rooftop solar has a great payback and the ability in time to effectively make money off grid services is again a great avenue for us to continue to invest in better buildings and better controls.
Absolutely. Cool. So I want to talk obviously about smart building technology, which we'll get on how you create flexibility in just a second, or how you're going to create flexibility. But I want to just talk a little bit more about, is there anything else like lessons learned on passive house, like building in that way, that you sort of haven't shared yet? Because I can't imagine you hinted at it with the procurement challenges, like getting an engineer to sort of design, but I can't imagine that's the only struggle you had in building a new way at scale. You said you did some big buildings in this way too. And I'm just picturing all the buildings that I've been a part of where doing things in new ways is always extremely, extremely difficult. So can you explain, what am I missing here?
Yeah, and it's interesting now. It feels easy, but it was so hard and it was years in the making. So we didn't single-handedly, there's other players in the space, but we had to kind of retrain the thinking of the industry and build up the capability. So we did it progressively in buildings. I'd do good insulation and air tightness in one building, did heat pumps in another building, till I had case studies in our own environment of all the elements you need to come together. And passive house, it's the classic Amory Lovins of you put it all together and you tunnel through the cost barrier. There's still quality buildings, so there's no doubt that these buildings cost more to build. They cost less to operate and they shouldn't come at a huge premium, but you're talking about getting your builder on the line for building a good building. And that's not always easy.
Yeah.
But the trick is to get your architect, your engineers, and your builder together to do integrated design. There's nothing new here. It's just very hard to do. And this is how every successful building that I've seen has worked. that they got in up front, and they said, okay, architecturally, if you do that, it's going to be very hard to seal up the building and insulate it. And engineering wise, if you do that, it's going to be too expensive to build. So having that dynamic, having the play, and I guess the easiest example for me was once we matured them up and we ran training courses and we egged them on, and we took the big construction companies and we pitted them against each other. We got one to basically pick up our first building, which was a timber building, CLT, cross-laminated timber. They wanted that building because the other big player in the market was building CLT and had the edge. So they grabbed our CLT building and they added passive house to it. And then guess who picked up our next passive house building? It was the other big player in the market who wanted to add passive house to their resume. So these companies came on the journey. They led it for it. We couldn't have done it without them. And it was the same for the consultants. They wanted that edge. But the trick was integrated design. And the really nice example, in the very first design meeting for our resi, the environmental, the ESD consultant sat down and said, all right, I know you want to talk about architecture. I know you want to talk about floor layouts and mechanical systems, but what we need to design up front is what fridge are we going to select for the units? Because every unit has a fridge. And if we got the crappy, cheap, inefficient fridge, it was going to cook the building.
Huh. Okay.
So it was almost the fridge selection that started to define the architecture, the layout, the engineering of the building.
Wow.
Because they're small spaces, so a fridge kicks out a lot of heat.
Yeah.
And what you want to do is manage heat. You want to manage it so it's not too cold. But if you put a source of heat in there, then you've got to add cooling to draw it out. So I'm overplaying it for the effect, but it was that kind of conversation up front. And the architect, we'd worked with him for years. He'd done a whole bunch of buildings for us. He was ready for the challenge. So we rolled with it, said, all right, let's go down to the local appliance store and find one that works, and we'll design the architecture around that.
Wow. That's really cool. That's a fun story. So, all right. So I think that kind of is a good segue. It's super insightful. Also a good segue into smart building technology, because I think if I had to sort of categorize like where we're at right now as a smart buildings industry, I think it's now like people are now wanting an edge by like design firms, general contractors, developers. The edge is now in the technology as well. So super efficient, super energy forward, but also super technology forward as well. I think that's going to be the competition line moving forward. Before we talk about the actual technology, though, I want to talk about, and this kind of gets at what you just talked about, it's sort of your role as the champion of technology for the university. So it's not just the energy champion, it seems like it's becoming the technology champion as well. And this is a core piece of my course. You and I haven't talked about this, but it sort of underpins each lesson in the course, which is here's the mindset and here's the role of the champion in overcoming the obstacles that our industry is so good at creating. So can you talk about your role in getting this program off the ground?
Yeah, that's a good segue, because I guess where we got to with these great buildings is you basically make them as passive as possible. The systems are super simple. We've got a bit of trim heating and cooling, and we've got a ventilation system, which are much, much easier to control when you full on VAV and all these reheats and dehum and all that sort of stuff, which is important but challenging. Mm-hmm. And I guess we got there through that integrated design. So my role in that process was to not be an expert in anything, but to know enough about every single little bit that when the architect said something, I'm like, this is how you do it. And it helps, like it's a throwaway line, but when you wrote the book, you can sit at the table and say, this is how you do it. This is where we've done it. And then they can't, come back and say, oh, you don't know what you're talking about. And most of the case, I didn't know what I was talking about, but it was just that confidence enough to say, you should go and learn this if you don't know it. And for me, it's the same in the smart building space. We very quickly hit the wall of, we had these amazing buildings, but I still needed to commission, I still needed to retune them. Just because they were these world-leading buildings didn't mean that the BAS system was any better than any of our other systems. And this is frankly where we fell down on these things. And we had this great opportunity with one of the buildings. It's an education building for IT and engineering. Mm-hmm. And the academic said, we want to use the building in our teaching. We want to show how it works. We want to expose the control. I'm like, brilliant, let's do it. But the journey to find all the systems, the journey to understand how we could expose that data, make it, you know, available, make it usable, make it useful for teaching and research was very, very hard. And I get into this space of we have these systems on our campuses and in our buildings that no one in the university actually understands and potentially doesn't even know they're there because, you know, the contractor comes in, they install some control circuit for AV or for a lift or some special little camera in a corner that does something, and then they leave and we have no idea what it is. And it's all proprietary, it's all locked up. So I guess the role of the champion is to.
You're right. It's got their sticker. You can call them if you want to figure out what it is. Yeah.
Yeah, but yeah, the call
call
itself
Bob
costs $100.
Exactly.
So it's getting that understanding together and getting people to view it as a system for me. You know, it's the same with the building. It is a system of heat flow. The controls are the same. And I guess the big hurdle for me was I had no IT background. So it was the gap between OT and IT. I was talking OT. I kept drawing these kind of technology stacks in my ignorance where I had the edge devices, the controllers, the sensors, the chillers hanging off these things. And I'd take it to my IT colleagues and say, I need this data to get here. And basically anything below the IP kind of layer, as I call it, you know, they were across servers and where it needed to sit. And is it on AWS? Is it on-prem? All that sort of stuff. Great. But they couldn't quite make the leap to these are edge devices. There's edge control. You want to run AI at the edge and you want to control a physical asset. They were great for a timetable system. They were great for managing enrollments, all these platforms that are native in the cloud. But where it blended with OT was a big challenge. And frankly, this is where the podcast has been brilliant for me because it's allowed me to lift up and to pick up the language to start communicating better with these people. So I guess over the last 2 years, it's been drilling into each of these systems, understanding enough so I could hold a conversation and then slowly piecing together all the different people to say, all right, you understand cybersecurity and what I need to do to connect this thing to the network. Okay, you understand that I've got a meter over here and all I want to do is get the data out of it into a platform that I can use it.
Yeah.
And, you know, these are my options. And the big challenge, which, you know, you early talked about in your podcast of about the sales hype or, you know, the marketing jargon is for years and years and years, we went to the vendors and said, how do we do this?
Yeah.
Which we got solutions, but we got lots and lots and lots of solutions and none of them talk to each other.
Yeah.
So the big challenge for us now, and I guess what I'm driving as the champion is how do we champion your language, not so much mine, because I feel like we're only on the start of it, but is how do we do it in a scalable and repeatable fashion? How do we make OT, as we call it, operational technology, enterprise IT? So rather than run my meter through a controller into a vast proprietary system and then try and extract the data out into a database and then try and translate it into enterprise analytics platforms, just pick the Modbus data up onto the IP network and dump it straight into enterprise IT platform because it's just numbers time-stamped and it's no different from any other data set.
Yeah.
But I've never had it there. Like I've spent years and years and years extracting data from the controllers because it was too hard to get it out of the database, and years and years and years of trying to backfill gaps in the data because the controller turned off because power loss or someone was servicing it. It's just not good data management, but I had no idea we were doing it so wrong.
Oh man, that gives me fond memories of early in my career. Lots of exports from Metasys and spreadsheets and plugging directly into a data logger to get the meter data, all that fun
And
stuff.
if you've got one building, that's fine. But if you're trying to manage a portfolio and you're trying to scale, and this is the opportunity for us, and this is the machine learning and AI opportunity, that we want to do it at scale.
Totally. So you guys have like a separate IT group, and then you have your facilities group, and do you sit in the facilities side of things? And so you're kind of bridging that gap a little bit?
Yeah, spot on. So we have an IT division and we have a property division, and eventually I annoyed the CIO enough that she agreed to appoint someone across our two divisions. So now we have this incredible lady that used to work in IT, worked for Huawei for a while, so she really gets this space. and she's half IT, half property.
Oh, okay.
And she's the translator. She finds the right people on each side and she brings them together and says, you need to do this.
Yeah.
And she's just been brilliant.
Love that. Love that. Yeah, that's part of what I feel like the champion doesn't necessarily need to be that person, but they need to have people in places like that they can go poke, essentially. Hey guys, just another quick note from our sponsor, Nexus Labs, and then we'll get back to the show. This episode is brought to you by Nexus Foundations, our introductory course on the smart buildings industry. If you're new to the industry, this course is for you. If you're an industry vet but want to understand how technology is changing things, this course is also for you. The alumni are raving about the content, which they say pulls it all together, and they also loved getting to meet the other students on the weekly Zoom calls and in the private chat room. You can find out more about the course at courses.nexuslabs.online. All right, back to the interview. Very cool. So you've talked quite a bit about access control and meters and building automation systems. So I'm wondering, before we get into the sexy technology, let's talk about the old silos, right? So given the fact that you guys are going where we're about to talk about you're going, driven by these net zero goal, you've probably realized, like you just said, like it's difficult to get data that you need to be able to optimize systems. You need to be able to hit these goals. And so what have you had to do from the standpoint of your contractors and your existing systems to make the data useful?
Yeah, so it's, again, one of those pivotal moments was we sat down with one of our building automation vendors, a local company, independent automation. They've been really great in terms of exploring this journey. But I said, in my naivety, I said, I want to make the BAS machine readable. And he's like, I understand what you mean. Let me just explain something to you. And he brought up a BAS graphic and it had a great floor plan and this incredible animation showing the chiller spinning and all these type of things. And, had all the data points on it. And then he said, all right, take away the picture. And what you've left with is icons located on a screen that are randomly named. And he's like, the data is there, but it means nothing without the picture behind it. So without the human matching the picture to the icons and the data, it was useless or nearly useless for a machine. It couldn't understand it. So we started on this journey of how do we start structuring the data so if you take away the picture, it still works. And the machine doesn't care about the picture. It wants to know the fan core unit is here, here, and there, and it's related to that. So we started on the journey of Haystack and we moved on to Brick. And I guess the critical bit was proving the value, because as anyone who's played in this space knows, it's not super mature. We're not at economies of scale here where you can just go and grab a data scientist and tag up your building. So we started tagging. The first one took us a year. And when I say us, someone who was much smarter than me doing it. Mm-hmm. And there's this great story. We did our second one and we did this great visualization and it's tagged up and you can see the relationships and showcase the floor. And in real time, we could bring the work orders together with the data from the field. We ran it into our enterprise analytics platform and we were starting to do all this great machine learning, because if you're in an enterprise platform, you've got real machine learning rather than some rules that a BAS technician programmed into your BAS. But I'm like, how come you only ever show me floor 3 of this building? And eventually he's like, we're still working on 1, 2, 3, and 5 because it just takes that long to tag it up when you don't have a big enterprise tool to do so. So I guess coming back to your actual question, as I vaguely remember it now, is this transition to make the data machine readable. It's been a long one. And I guess we're at the point now where we're feeling confident that we have done enough to prove the value at individual pilot level, at a couple of building levels, at DER level, our solar and our batteries and those type of stuff. And now the big challenge, the big opportunity for us is, how do we do it at scale? How do we build an industry around this and bring it together?
Cool. And that's sort of to be determined, next steps, basically.
That's the challenge that is right in front of us now. I've got some pretty solid ideas of how I think we do it, but I guess being on the passive house journey, being on the electrification journey, the biggest thing I've learned is you need enough confidence to move forward, but don't think for a second that you've got the answer because you need to keep learning every step of the way. You just need to know what you're going to do next and know where you want to get to.
That's another champion mindset. I love that. All right. So you sent me this document. It is I don't even know what the platform was. It's like a note-taking platform.
It's in Miro, and I only say it because we're all working virtually now, and Miro has been an incredible platform for us to whiteboard and stitch ideas together.
Yeah, absolutely. I think I'm going to start using that. So can you explain, first of all, what is the name of this thing? And can you explain what it is?
Yeah, so I guess I talked about having to map out all the different systems, and I talked about that education buildings before. I started chasing down, and Kieran did a huge amount of work for us here of mapping the different systems, and Kieran dutifully wrote out this diagram that showed all the systems and exactly how he would present it as someone from the BAS world, and I put it in front of the IT people, and it didn't make sense to them because they view the world very differently. Think about it as a virtual whiteboard. We started mapping out these clusters of information and where they sit. Very high level, we have at the top what we call the sort of the common building data layer, or data clearinghouse is what we're kind of aiming for. We have all the ubiquitous building data. So this concept of energy data, which we know is in every building and is relatively easy to get if you do your homework, and it tells you a lot. It can tell you whether a fan's failing. It can tell you whether people are comfortable because you can see how much cooling and heating you're using. It can tell you occupancy levels. There's so much richness in the energy signature if you have the right tools to use so. Then there's things like Wi-Fi, things like weather, car park occupancy, these things that give you predictions around how busy your building's going to be. Do I need to start ramping up? Timetable bookings, all those type of things. So data sets that are common to every building is what we're trying to pull together at, I guess, a campus level, or as I call it, the enterprise level. So it's kind of sitting at the top of this diagram as we're drawing it out. So imagine kind of a cloud up there. The idea is to get that data together, normalize it against space, because space is what it's all about. This chiller, this energy, this Wi-Fi, this WAP, they all relate back to this room or this space. So space is the index, and obviously time. But you have this concept of this sort of smart platform at the top that ideally then you can start to plug into the cloud. So, there's a whole bunch of cloud providers out there, but as we know, for anyone who's tried it, getting your data into their world is a challenge. And ideally you want to make it as easy as possible. So you kind of get into ideally a plug and play environment. So rather than doing a major data transformation every time you want to try a new vendor, the data is there, it's already organized, and it's a relatively simple transformation to start using their analytics or their new AI or whatever it is. So I guess that's the kind of data clearinghouse that sits on top of everything that, at a campus level looks over it. And I guess once you add intelligence to it, you can kind of think about as the brain. And then sitting underneath that, you have these different elements that make up a campus.
Wi-Fi would be used to do what with? Count people?
Yeah, proxy for occupancy. So it's terrible at counting individuals, or at least it's challenging to count individuals because you get into a whole bunch of privacy concerns, and there's bleed. You can pick up people across buildings and all that sort of stuff, and then people bring in 4 phones one day, and you get
Someone's
effectively
got
you get connected.
an iPhone and an iPad and a laptop, and yeah, okay, yeah,
exactly. So, but it gives you a proxy, and that's what we need for buildings. We need to know relatively how busy is the building. And last time I saw this many devices connected, I needed to crank the chiller at this type of range or whatever it is.
I see.
So Wi-Fi is a really useful proxy, and I guess we've seen, particularly through COVID, that it's been really useful for understanding social distancing, the scheduling, and understanding, I guess, the relationship between occupancy and buildings. And anyone who's been looking at their buildings knows that you can only, with a traditional BAS system, you can only turn your building down so much and keep it open. So we had this example where we had students come in for exams, energy went up, the Wi-Fi correlated beautifully, the data was great, and then the students went away, and it's still 80% of the energy was humming away in the building because we just couldn't turn it down partially. It's kind of on or off because that's how the building's been designed to run.
I see.
So I guess using those different proxies to be able to predict, if the car park fills up by 9 o'clock, we know that the library's about to get smashed. So we start to turn it up, is the theory. We are not there yet, but that's the kind of premise of bringing this common data set together.
I see. Cool. And you mentioned tools for analyzing energy profiles. Are there any that you would be able to say out loud, or?
Yeah, definitely. And James and I had a quick chat about probity and procurement, but in this case, it's relatively public. We've done a trial over the last 18 months with NG and C3. So NG have this huge partnership with Ohio State and now Iowa State, but effectively they developed out this platform called Smart Institutions, which is at that campus level, and the idea of bringing buildings together and using C3's AI tools. Effectively, you can feed the data up, and they can do that energy analytics at campus scale. They can do the forecasts. They can look for the anomalies. Track your plant and stuff. And there's a whole range of other companies, of course, out there that do it. This is just the particular partner that we're excited about and have been doing the trial with. But I guess it is that high level vision and the intelligence that you can put at that kind of brain level of the diagram.
Got it. Cool. All right, proceed.
So then sitting underneath that, we have the different elements that make up the campus. So we have the buildings themselves. So imagine a collection of smart buildings. And at this stage, we're primarily working in Niagara or N4, and we're currently doing a massive migration, as we call it, from Envision, from Continuum, from the many different systems that we managed to collect over our BACnet years into our system. We thought that if it was BACnet, then everything would seamlessly stitch together. We were so wrong. So I guess we're doing Niagara either native into the building or overlays. We're doing virtual Niagara overlays over Envision and Continuum in some cases. But effectively, you have this collection of smart buildings sitting under this common data layer. You have an edge system where things like solar for batteries, for EV chargers, effectively putting a controller at the edge so you can aggregate the data, but also have some intelligence there to ramp it up and down, to take a signal from the centralized intelligence to say, all right, we all need to turn on, we all need to turn off to respond to the grid. Mm-hmm. And I guess the example here, we're not using it. We're actually working with Indra and their Flex platform on this, but probably a common example that some of your listeners might have heard on is the Voltron environment.
And by the time this goes live, we have a deep dive coming up about Voltron that people will have heard.
Great. So that ability you don't need a full-blown BAS system and all the licensing programming that comes with it, but having a PLC there that you can put some intelligence into, a little Dockerized computer basically where you can write up your scripts and put it at the edge there is great. Then obviously we have the asset management bit. So the work orders, the asset registry, all that type of stuff that sits together in a cloud with the investment sort of sitting off it. So I guess building up the picture of the diagram that you referred to is we kind of have this kind of campus brain at the top, and then we have all these distributed intelligence bits sitting under it, or at least we're working to it. And it became so big and unwieldy that eventually we started calling it the Kraken because it looks not dissimilar from an octopus. And to stretch the analogy, octopi have this incredible intelligence. They're effectively a mollusk. They're the same as an oyster in terms of their lineage, but they're super intelligent. And amazingly, they have a great brain, but many of their neurons are distributed around their body. So it's a really great analogy because you have the legs and then you have the thousands of tentacles, and the tentacles can operate independently of the brain. The suckers can independently operate from the tentacle from the brain. So it's this organism that's incredibly smart that has this distributed intelligence. And that's kind of how we're viewing this diagram and our campuses, that you have this central bit where decisions are made for the whole and the collective, but you also allow the tentacles and the suckers to do what they need to do at the edge to allow the overall system to work well. And I guess the stretch of the analogy is that someone dropped this on me the other day, which was really nice, that the other thing octopi can do is if they lose a leg, they can regrow one.
Okay.
And in this smart building world where things are learning and we're evolving, we make mistakes. And there's stuff that we're shelving. You've talked about it before, mothballed intelligence, or the concept of analytics on the shelf. There's a whole bunch of stuff we've done that, we're undoing now. We're re-emerging and regenerating. So it's become very fond, and certainly it's been picked up enterprise-wide that the Kraken, we're working on the Kraken.
Working on the Kraken. Oh, that's awesome. And that reminded me of this amazing documentary on Netflix called My Octopus Teacher. I just wanted to say, if anyone hasn't seen it, it exposes my little bit of my freak that I haven't exposed on the podcast, but people should definitely check it out. Cool. Okay, so what's the status of the Kraken and sort of rolling it out in all these different? I'm gonna just try to guess here. I'm assuming you're trying to like fund it as different projects like you have the roadmap where you want to get to in the end. And so what I'm used to doing is trying to basically shove it into all these different places and hope that at the end it all comes together at some point. Is that the approach, or is it like the dream would be that someone just funds it all right now? So what are you up to right now?
Yep, no, that's it. And the dream would be that someone could come and do it all for me. But the reality is that it's hundreds of people that need to get on board to help make this a reality.
Yeah.
The status of it is that I think we've proven out the value of each of the different elements, and not at scale, but again, very small Kraken at this stage. And we've got a kind of couple of buildings, a couple of case studies here and there, just like we did with the kind of net zero building program. So I guess the 4 layers that I describe it as is, that common data layer, the smart building layer, where individual buildings need to be intelligent, they need to be autonomous, and then they need to be able to talk to the campus and talk to the grid. The work order system, the asset management, it needs to be smart enough to keep the automation working. So I guess It's basically saying you have an autonomous car, but if your camera stops working, you can't drive the car anymore.
Yeah.
So the work order system, the asset management system needs to keep that camera working and online at all times so the car can be autonomous, and the same with the building. So there's the piece there around the smart asset management. And then the bit I alluded to, which we refer to as our microgrid, is the distributed energy resources, the management, the coordination of that. And when I say DER, it is batteries, it's solar, it's EV, and then the buildings themselves become DERs, if you will. Like from a building point of view, horrendously complicated, bespoke, needs to know itself and needs to have an AI dedicated to itself. But from a microgrid point of view, it's just another energy resource that it can communicate to and say, can you give me some kilowatts right now, because I need to respond to the grid.
Yeah.
So it's that kind of concept of the buildings sit in the DER world with their own embedded intelligence. And the analogy here is, if you think about a VRF system, it comes in with its own inbuilt controls. It can operate itself intelligently, efficiently. But if you network it and you say, hey, the VRF just across the road's doing this, you might want to try it. That type of sharing is the concept there.
Sort of like orchestrator, because Voltron could be capable of that, but you're talking about all the systems being autonomous. Voltron has intelligent load control at this point. Is that kind of what you're talking about, where I'm telling Voltron how much capacity I need or how much capacity I have, and it's making the decisions on where to send stuff?
Yeah, forgive me if I misstep on Voltron, but how I see Voltron,
just that layer of the stack. That's an example.
Totally
would fit there.
We've got some colleagues and other unis across the states that are using it that we collaborate with. And I guess it's equivalent to our Indra. We have nodes, which are basically like the Voltron devices, and the IndraFlex supervisor. So what it does is it allows you to communicate and data aggregate. So it's not dissimilar from N4 or supervisor basically. And then what we're doing is effectively coding it up the algorithms to do the control on top of it. Mm-hmm. So it pulls the data together and says, this building's doing this, and we've got 20 buildings connected and a bunch of DER connected to it at the moment, that you can get a picture of the world. And then, in the cloud or wherever you put it in your server, you can run the analytics and say, right, this is what we should do. Mm-hmm. Then effectively the idea is, and we're not quite live yet, but we've been playing, is that you go out and you make a deal with each of those DER and say, can you do this for me? And then you aggregate that deal together. So the devices need to be smart enough to know what they can and can't do to maintain comfort and all those type of things. Doing DER by changing comfort doesn't make sense to me in terms of why would you make your occupants uncomfortable to save a few dollars. But if you can do it in a way where you can save a whole lot of dollars and the occupant is still comfortable or is willing to accept it, is great. So you have that coordinated intelligence sitting on top of the microgrid network. And that's something that we've been working up in-house and working with Indra on. But there are great examples out there of applications that are starting to emerge that if you can plug in, you can do this commercially.
Is the grid interaction piece of this, is that sort of still in the future, or are there any pilots around that at this point?
Yeah, so that's the one. So we're working, I guess to your earlier question, we're working on all of these bits at once and limited resources. But the grid interaction, we were hoping to get the trial up this summer, but we've had a really mild summer, which means that we haven't actually had a lot of peak events. And that last 10% of integration is always the hardest bit.
Totally.
But I guess we have a retail agreement in place where if we get a peak event and electricity spikes up to $1,400 a megawatt hour, then basically the deal we have with our retailer is if we can save a megawatt hour, they'll give us half and they'll take half. So basically it reduces their exposure and we get the money as well. We get the other half of it. So the idea there is that by aggregating, we have the signal from the market, which is kind of coming from that common data brain bit that we can see, okay, there's a peak event coming up, the market calls for demand response, and we discharge our battery, or we turn down, or we crank up, whatever it needs us to do to start to help the grid, and in doing so, save ourselves some money. But I guess the bigger goal there is the more flexible our buildings are, the more renewables we can accommodate in our grid, and the quicker we get to this world of demand and response following each other
yeah,
renewables.
Totally. So are you thinking about like sort of tracking and quantifying flexibility in any way? And do you have a like theoretical maximum flexibility and kind of where you're at right now? How's that work?
That's exactly what we're working on. So a battery is easy because it comes out of the box and says, this is how much flexibility I have.
Yeah.
But a building is not so easy. We had some engineers have a crack at it and they gave us a very disappointing answer to that question because they were looking in traditional bounds and they were using traditional control. So this is where we're starting to look at products. You've had them on the show, Brainbox AI. We're talking to them at the moment, amongst a bunch of others, but they're working on this concept that if they can predict 2 to 3 hours into the future for chilled water demand and the airflow, then they can start to say, well, I'll start pre-cooling, or this is how much flex I can bring into the building. So I guess where we're at right now is not quite there. We're looking to trial those in the next couple of months. But what we're doing is kind of manually testing the buildings with our talented BAS technicians to say, if I pull this lever and I push that button, how much flex can I get before the building starts to squeal? And we're bringing in our behavior change researchers and to engage with the occupants to say, well, what are you prepared to endure? And we don't want them to endure much, but effectively we need them to be cognizant of what we're doing and basically use them as the test environment to say, how much flex can you pull out of a building? So we can answer the question that you asked. A typical building can shed comfortably 10 to 15% of its demand for half an hour, or if it's 2 hours and it's only 5% or whatever that is. And as we know, every building is different. So we need to tune that response to each. Right now, we're kind of selecting from a program to say, based on the response we need from the grid, we'll take program 1, 2, or 3. Yeah. But the goal is to allow the intelligence of the building to say, I can give you this much if you do this for me.
Cool. You guys sound like such a great partner for someone like Brainbox or other startups that are trying to get these newfangled technologies off the ground. You guys sound like such an amazing client, which would be fun to work with you guys.
Yeah, I want to pick up on that because absolutely, I agree with you there, James. But this is what we're doing this year. So I guess we've got a couple of buildings tagged up in brick. We've got 20 buildings loosely tagged in Haystack to interact with the microgrid piece. We've got our workflow system and some of our buildings connected into our enterprise analytics system, so we can start to do the asset tracking and critically making sure that when a work order is issued that it's actually fixed, track the data after it's fixed rather than just pay the ticket. So we've got the start, the bones of it. We know we can't scale on our own. So we've got a call out to the market right now to say, come and work with us to do a test and learn. So the goal for the next 6 to 9 months is to test and learn these applications, these data structures, and say, we've seen enough that we know there's value here, but can we really stitch it together? So the call out there is to companies to help us scale our data model. How do we scale the tagging? How do we make that more efficient? How do we make the buildings more flexible? How do we make that DER piece work? And like I said, we've trialed it all ourselves, but the goal now is to allow the market in and say, if you've got the idea in the will, come play with us. We're trying to create this innovation environment so we can help solve this and help other people follow and help other people come in and say which bit worked and which bit didn't work, and we'll do the bit that worked. And as a university, we'll take the hit and the learning because that's what we do, R&D, on the bits that didn't work.
I love that. Obviously, that's a great announcement to make on the podcast. So hopefully you get some people reaching out to you, which I'm sure you will. Cool. All right. So besides that piece, that exciting development of all these Nexus nerds that are about to reach out to you. What else are you looking forward to this year?
So a big thing that's been wonderful, and I'm sensitive about it, but off the back of last year, homeschooling and all those incredible experiences that came along with lockdowns, Australia's in pretty good shape. We're an island, so we've contained it. In many cases, there's Australians that can't get back yet because the borders are pretty tightly closed, but we're almost COVID free. We have these little outbreaks, but it's getting back to normal life and getting back to using buildings properly and the learnings that come from it. I mentioned before that our buildings were set and forget. We designed them to be always on because we had students streaming in. We never had enough space. Whereas now it's this, I guess, it's a coming of age. All the things that we were planning to do are now needed and kind of justified in the new market. We need to be able to show that we can bring fresh air into the building consistently. And we need to be able to ideally have flexible buildings, not just for the grid interactive, but because people are using them differently. I'm working from home today. I was in the office yesterday. I'm in the office again tomorrow. So I'm working where it best suits me. And this is where I guess our students and our staff are doing so as well. So I guess bringing that together, last year, the executives saw the power of data because they had to all of a sudden turn their business model upside down, and knowing what the students were studying, knowing how many people we had on campus, they got used to data and they saw the power of it. And our COO came and said, how come I can't have that data for my buildings and my entire estate? And I said, well, I'm working on it. But it's this great position where all these kind of value propositions that we had around smart buildings, which were, if I'm brutal, were mostly branding before, and now in demand. If you said that you could help wayfind and you could space people out in the building and people could customize and be flexible, people would be like, who cares? I don't have enough space. I'm just renting it out anyway. Now we've got buildings that need to reimagine themselves, and the smart building technology that we're working on is, for me, the pathway there, and the demand is coming. I guess the business case, I think, is growing. So I guess I'm keen to see, can we scale this, and can we make it commercial? Because our mission is to transition the world to renewable future, so it's sustainable and comfy for people. So I see that there's this great shifting point where we can start to do that because the real estate sector is ready for it and calling for it.
Yeah. So this audience and just the wider smart buildings community as well, there's such a focus on office buildings that people forget that there's whole other industries that are being disrupted as well. Like higher education is one, and we can't forget how much that's being disrupted right now. So that's such a great point. Well, cool, Rob. This has been super fun. We talked about Octopi and a bunch of other topics I didn't expect to talk about. So thanks so much for coming on the show and sharing your insights.
Wonderful. Thanks for having me. It's, you get down in the details so often that it's really nice to pull up every now and then and remember what the whole point of it is and see it from that sort of helicopter view. So likewise, super fun. And certainly thanks so much for the podcast. It's helped to shape the journey we're on. And I look forward to the upcoming episodes as we continue on the journey. So keep up the good work is, I guess, what I'm saying. Thank you.
All right, friends. Thanks for listening to this episode of the Nexus Podcast. For more episodes like this and to get the weekly Nexus newsletter, which, by the way, readers have said is the best way to stay up to date on the future of the smart buildings industry, please subscribe at nexuslabs.online. You can find the show notes for this conversation there as well. Have a great day.